Welcome to the top 3 of our Rado lecture. So in the past 2 talks, Professor Wang has been undertaking a heroic task of explaining the solution to the sticky case of the Kakeya conjecture, and then today he should kind of do scans and welcome Professor
Wang. Thank you very much for the nice introduction. Thank you very much, everyone, for coming to the last talk. Today, I'm going to spend the first 10, 15 minutes or so just trying to tell us, to discuss a little bit some of the ideas goes into the proof of the sticky Kakeya problem. And then later, we'll turn to our last paper, how to use induction on scales and how to set up induction to generalize the sticky Kakeya theorem to prove the whole conjecture. So yeah, so I think it's in the afternoon. Let's warm up with some pictures. So last time we said that the key property of the only, like, the most important place where we use the stickiness is that in the sticky Kakeya, for sticky Kakeya set, any extremal sticky Kakeya set would look like a union of those parallel slabs. So I don't know if you can see this very well. Okay, let me try to show you some previous pictures. So let me remind you, like, this is the key property from the stickiness, means that it should have some rigid structure. In particular, the Kakeya set, which is a union of delta tubes, with the set of delta tubes satisfies certain non-concentration properties, Wolff axioms, and those at all scales. And the union of those delta tubes intersect each delta to the 1/2. Oops, it's not here. Intersect each delta to the 1/2 ball is going to be a union of parallel delta to the 1/2 times delta to the 1/2 times delta slabs. So that is the structure of the sticky Kakeya set that we spent a long time in the last talk to deduce it from this key property that if a fat tube passing through a point in the sticky Kakeya set, then there must exist a thin tube inside this fat tube passing through this point as well. And we deduce from this key property in the special case of the Kakeya sets in R3 that a sticky Kakeya set should look like a union of parallel slabs. And then there are many intricate pictures that I didn't describe. So these pictures would eventually lead to a sum product type phenomenon. So let me first show you what this sum product type configuration is, and then I will show you where the 3 sets A, F, and G come from the Kakeya set. So the sum product configuration is that we first have a subset of A, and the dimension of A is equals to the dimension of the Kakeya set, of the sticky Kakeya set minus 2. So remember, we want to prove that any sticky Kakeya set has dimension 3. So the goal is to show that this set A has dimension 1. And what is A? So previously we said that a sticky Kakeya set inside thick ball is a union of parallel slabs, but we don't know how many slabs are there. So suppose there are, like, these slabs fill out this ball, then we are happy because it means that locally the Kakeya set is 3 dimensions. So the A is going. So first of all, inside this fat tube, we can see a bunch of parallel slabs. They are parallel within each ball, but their orientation could be different. So when we do anisotropic rescaling, we map this thick tube to a unit tube. So this tube has radius 1. Then each of those parallel slabs, we call them slab grain, is going to map to horizontal tube, and those tubes are parallel on each horizontal slice, but they might have different slope at different slices. So A here, A is going to be the location of those horizontal tubes, let's say at height 0. So the A is just the x coordinates of those tubes. So that means this explains why the dimension of A equals to the dimension of the Kakeya set minus 2, because A is this x coordinate, and we have one dimension in this direction, and also we have one dimension in this direction, because all the tubes are like away from horizontal. So just to give you some intuition, A is the location, and now what is F and G? So now this sum product phenomenon says that F is going to be a one-dimensional set in the plane. So F is small f, z, and z. Z means the height. So this z means the height of the horizontal slice. And so this is like z. And what is fz? Fz is just slope of the horizontal tube. So sorry, it's probably not so clear. So these are supposed to be horizontal tubes. It's dark red here. So fz Kakeya set is organized into union of parallel slabs. And after rescaling, this is still another extremal Kakeya set. So we can apply the same argument to say that at this box, it is again a union of parallel slabs for the extremal Kakeya set at a different scale. And G is going to be sort of the slope of so G is the slope of the other direction. So this is, sorry, this is Gy. So when we do change of variable, we assume that this is y-axis, then those slabs will have, they are parallel inside each fat cube, but they might have different orientation in different cubes. So this small gy will tell you the slope of those slabs, or the direction of the slabs in different cubes parameterized by the y direction. So, and then we have the sum product phenomenon tells us that the set A plus F minus F dot product with G is again in A, where F minus F dot product with G is defined as Fz1 minus Fz2 times Y plus Gy times Z1 minus Z2. So, okay, let me just tell you where this equation comes from, although I didn't do any calculation. The calculation of coordinates come from the previous page. I think the slides are online. You can check it out if you want. But let me just show you where does this sum product configuration come from. So we first start with, let's say, okay, let me choose a color. Okay, we first start with some location here, let's say some point A, and then we go to a certain height, let's say Z1. This is Z1, and then we go along this horizontal tube to some distance, to some distance y, and then we go downstairs along the same those slabs, those yellow slabs, to height Z2, and then we go along the horizontal tubes at the same of the same height, and to y equals 0, and then go downstairs. So go down to get another A. So this means that this, like, it's like someone is traveling we are only allowed to travel along those horizontal tubes and also those slabs that's given to us for the sticky Kakeya set at a different scale. So this trajectory gives us the sum product configuration. And yeah, I know this is just, how to say, I didn't show you any calculation, but I hope that this picture makes you feel like the sum product configuration is not that strange. So now we need to analyze this sum product configuration. The plan is to say that using some projection theory, we are going to show that either A has dimension 1. So either A has dimension 1, and we are done because we just said that the dimension of A equals to the dimension of the Kakeya set minus 2, or the F and G should lie on orthogonal lines. So F and G, they are like graphs. So we can see that if F and G lies in orthogonal lines, then F minus F dot product with G just give us one single point. So that is the goal. First, we want to use projection radio. Later, I will explain what radio projection is. We want to use projection theorem to show that either we are done or we are in a very special case with even more structure. That is, the slopes are changing in a very predictable manner. For this picture, or even what does this sum product configuration mean? Okay, so last time we said that it's the reason why improving Wolf's 5-halves bound is difficult is because it's very hard to distinguish the Heisenberg group and the Kakeya and the sticky Kakeya set. And we should comment that even when we arrive at this sum product configuration, which seems quite unlikely, we still haven't distinguished the Heisenberg group and the sticky Kakeya set. So here is why. So for the Heisenberg group in C3, we can take A equals to R, so the A being real numbers. So this is not, so it has dimension 1/2 of the complex numbers. And then we can take F to be Z bar comma Z. And so as we can see that F has the complex dimension 1 because Z is allowed to take in to be any complex numbers. And then F minus F equals to F because Z bar minus Z bar is still Z bar. And also we know that F dot product with G equals to like some complex number plus its complex conjugate. So it lies inside R. So this means that A plus F minus F dot of product with G equals to A. Equals to A. But however, this A does not have 4 dimension. In other words, we really need to do something to say that there is no Heisenberg group in R3 where our sticky Kakeya set lies. And this is what we are going to do. We are going to use radio projection theorem. Are there any questions? Is it clear that the Heisenberg group examples satisfy the sum product configuration, but A does? So first of all, A does not have 4 dimension. Also, this F and G does not lie on orthogonal complex lines. Well, so first of all, this F does not lie on any complex lines. Okay. So because I think this is a quite important step, that this is the step that distinguishes the sticky Kakeya set. So I want to emphasize what tools we use. So how how to analyze, let's drop the A. We are going to show that either F minus F dot product with G has 4 dimensions, or they lie on orthogonal lines. And then, so how do we think about this sum product configuration? So first of all, F minus F is just a set in R2. We can fix a point, or in other words, a vector in R2. So this theta is just F z1 minus F z2 and z1 minus z2. So for any vector, we can define the orthogonal projection pi theta. So from R2 to R, given by any point P maps to theta dot product P. So let's say this is the direction theta, and then any P here is maps to this point, P dot product with theta. So there is this classical Mass-Jones projection theorem, tells us that for any compact subset or for any Borel subset, for Lebesgue almost every theta so even though here I said in S1, but you can renormalize so to accommodate any other vectors in plane. So for almost every theta, the dimension of the projection image, the dimension of pi theta G, equals to the minimum of the dimension of G and 1. This is the optimal bound, because when we suppose we have a set and we project to some lower dimensional space, we cannot possibly increase the dimension of the set if the set is like compact. And also 1 is the dimension of R, so we cannot have a dimension greater than the dimension of the ambient space. So Mass-Jones projection theorem tells us that pi, if we allow us to project in most of the directions, then we have good projection estimate. Now the next question is, how many directions are there in F minus F? So here, as we can see that if we take a theta in F minus F, then theta dot product with G just give us pi theta G. So pi theta G is just theta dot product with G. So the next question is, we need to ask, how many directions are there in F minus F? So this is the radial projection problem. So now F is some set here. And what does it mean, directions in F minus F? It means that we take another point, one point in F, and then we take all the directions that we can see from this red point to other point in F. Well, now I sort of draw F as a closed curve, so it's kind of obvious to see that there are all directions. Let me try something else. So we can also say that, okay, there is one bad case, is suppose F is a line, then no matter what point in F we take, we are only going to see one direction, right? So we are only going to see this direction. But suppose F is not a line, it's not contained in a line, then it could be any fractal set. But the theorem says that if F has dimension 1 and it's not containing any line, then there must exist a point in F such that we see many directions. So this is as if we have some light on the ceiling, and then we want to see, someone is standing here and we want to see, this is radial projection in 3D, we want to see how large is the shade. So this is the radial projection theorem we proved joined with Thomas Oppon and Pablo Schmerkin, says that if F is a subset of R2, so this R2 is going to be important, and the dimension of F equals to 1, and F is not containing any line. So here it says that if F is contained in a line, then it only determines one direction. Then F minus F determines a one-dimensional set of directions. So says that this should have one-dimensional set of directions. This is the theorem that distinguishes R and C, because for the Heisenberg group H in C2, the F is Z. Okay, I think I put Z bar in the wrong place. It's Z bar and Z. Then this F minus F only determines one real dimensional set of directions instead of a complex dimensional set of directions. So that means that this statement is not true for sets in C2. So using radial projection theorem, using this theorem, we say that as long as F is not contained in any line, then F minus F determines a one-dimensional set of directions, and then combined with Marstrom's projection theorem, we know that we have a one-dimensional set of direction theta, so there exists a theta such that theta dot product with G has dimension equals to the dimension of G, which is 1. So in other words, we show that either F has to be contained in a line, or F minus F dot product with G has dimension 1. In other words, this says that this guy has dimension 1, and A plus a one-dimensional set should have dimension 1. So this says that the Kakeya set has dimension 3. So that is I think that's the crucial step that distinguish Heisenberg group and sticky Kakeya set. And now that we know F lies in a line, then it's not too hard to see that G has to lie in the orthogonal line, otherwise we are dumb as well. So suppose G is here, then it's kind of obvious to see that F minus F dot product G contains a segment, and we are done. So in the very special case of F and G lie on orthogonal lines, so we have a lot more structure, and there are some other projection theorems that could be applied, but I think I will skip it for now. But at least this intuitively says that the problem somewhat becomes easier because we have more, we know more about the sticky Kakeya set. And also at this point, we have ruled out the bad example. Okay. Yeah, I'm going to switch to talk about how to generalize the sticky Kakeya theorem to prove the whole conjecture. But before I move to the next topic, are there any questions?
So in this step, we show at the bottom of the stats,
Yes.
Organized grades with very dense.
Yes. It's so when I say bottom, it should be just a typical slice. So in reality, it should hold for every slice. And so that's why it has dimension 3. Are there more questions? Okay, so let's summarize what we have done. We show that suppose T is a set of delta tubes contained in the unit ball. And also suppose T is the set of tubes is sticky, which means it satisfies the Kastar-Wolff axioms at all scales. Then the union of tubes has volume approximately than the number of tubes times the volume of a single tube. So this is our sticky Kakeya theorem. And the next goal is to remove these 3 words to say that if we know the set of tubes satisfies the Kastar-Wolff axiom, then the volume of their union should be approximately the number of tubes times the volume of single tube. In other words, if the set of tubes satisfies the Kastar-Wolff axiom, I will just remind you what it means. So it means that for any rectangular box, U, the set of tubes contained in the box shouldn't be too large. It's less than the volume of U divided by the volume of a single tube. This is a necessary condition to say that such bound holds, to say that the set of the tubes are essentially disjoint. So this volume bound is equivalent to the following multiplicity statement. So multiplicity means the number of tubes through a typical point. So this volume lower bound is equivalent to say that the number of tubes through a typical point is bounded by some constant. So similarly as before, the induction hypothesis is to say that suppose we know if the set of tubes is Kastel, satisfies the Kastel-Wolff axiom, then the multiplicity is bounded by the number of tubes to some sigma, where sigma is for some positive sigma. And it's the same as last time. When sigma equals to 1, this is trivial. And then the goal is to show that sigma equals to 0. We have seen this picture last time, so, but we are going to see it again. So this is this how to go from sticky to general case. So we assume that if the set of tubes is sticky, then we are done. So we assume it's not sticky. So remember from the non-sticky picture, we see a lot of, let me try to show you where is this. In this non-sticky picture, that's the left-hand side, we see a lot of T-row. So we see a lot of those purple tubes. So that's the image we should have in mind. In the non-sticky case, there are a lot of row tubes. So when we want to, now that we want to generalize the theorem from sticky Kakeya to non-sticky, so we can just assume T is non-sticky, so we expect then we have a large number of row tubes. And we again look at the multiplicity. So here, so we have the first decomposition of the multiplicity, mu T is approximately the number of, so this is mu T, is approximately the number of thin tubes inside a thick tube passing through a typical point, and then times the number of grains passing through a typical point. So the grains means that when the thin tubes inside a thick tube intersect, since their angle separation is too small, they in fact intersect into a tube segment. So here the tube segment has length delta over rho and radius delta. As before, we know that this holds in general. And so previously in the sticky case, we say that, okay, the second decomposition has to be the same, has these two things has to be equal, so they should be the same. But in the non-sticky case, this cannot possibly be true because we have a lot of row tubes. So we expect a lot of row tubes passing through each point. And this second decomposition is wasteful when very non-sticky. So even if we apply, so the second decomposition is the following: mu T is less than mu T T rho times mu T rho. So in the second decomposition, even if we apply the best possible bound for the multiplicity, the number of row tubes through a point, this is going to be still too bad. And that is the key difficulty in the past when people think about the general Kakeya problem, is because in the non-sticky case, even the best possible bound is not enough. And then how do we think about those non-sticky Kakeya set? The answer is that we should think about the first decomposition, because the first decomposition is approximately the same, so it does not have any loss. But why people didn't think about the first decomposition? It is because those grains, those blue segments, they do not have any a priori structure. And so they could be any set of tubes that's come from the Kakeya configuration. So the difficulty for the first decomposition is that we have no control on the grains. So it's the same. The only thing we know is that since the grains has length delta over rho and radius delta, so if we focus on, if we focus on those grains inside a delta over rho ball, and then rescale everything to a unit ball, then this becomes rho tube. And as before, this rho tube so it is this rho tube we should study rather than the original fat tubes. And I think the key ingredient for the generalizing sticky Kakeya theorem to arbitrary Kakeya set is that we were able to apply some scale decomposition or factoring proposition to study an arbitrary set of rho tubes. So here we say that when we study the grains, the main difficulty is that we don't know anything about the grains. So what this factoring proposition tells us is that yes, given us an arbitrary set of rho tubes, like grains, we can still find the structure from no structure. And that is the power of this factoring proposition. And it was inspired by Shmurkin's multi-scale decomposition. This is also the crucial idea that underlies the recent developments in geometric in projection theory in the past 5-6 years. Also, so I will try to explain this by this picture. I found it online. So suppose we have a messy set of spaghettis, and we want to put them into envelopes. We want to organize them. So for this set, so if then they are organized as such, then it's kind of so we can just put two boxes, like one here and one here, there, and then we can pack them nicely. And how do we describe it in proposition? It says that the following. So for any set of rho tubes contained in the unit ball, there exist two numbers, A and B, greater than rho. So the two parameters A and B are not given. So we don't get to choose. So this A and B are given to us by the set of rho tubes. There exist two numbers and a set of A times B times 1 boxes, a set W of A times B times 1 boxes, and a significant subset of T. We cannot do it for the entire set, but it's usually harmless to replace by a significant subset, such that the W itself satisfies the collection of those A times B times 1 boxes satisfies the Kastel-Wolff axiom. And so this means that so those large boxes are W, A times B times 1. And when we say the collection of large boxes satisfy Kastel, it means that for any even larger box, U, the number of W's containing U is less than the volume of U divided by the volume of W. So it's the same definition replacing, previously it was about a set of tubes. Now we just replace tube by any boxes. So first of all, we know that W satisfies the Kastel-Wolff axiom. And then second, for any A times B times 1 box, the set of tubes contained in the box satisfies the Frossman-Wolff axiom within this box. So this means that for any boxes that's smaller than W, the number of tubes contained in V, so is less or equal than the volume of V divided by the volume of W. So this is a renormalized Forssman-Wolf axiom. The volume of V divided by volume of W times the number of tubes contained in W. So I hope you can still remember, like the theorem we are trying to prove is that if something satisfies Kakeya-Wolf axiom, then they should be essentially disjoint. And if something satisfies Forssman-Wolf axiom, then they should fill out the box that contains them. So in other words, this proposition combined with the theorem we hope to prove says the following. For any set of row tubes, we can find some boxes or some envelopes to cover them. And the boxes themselves are essentially disjoint. And the row tubes will essentially fill out those boxes. So this is a structure theorem that tells us all the information about union of tubes in R3, up to some refinement. So are there any questions? And this is it, because of this factoring proposition, we can find those like structures about collection of tubes from an arbitrary collection of tubes. So that is our starting point for the proof. We are going to apply the factoring proposition for the set of those grains. And we are going to study the multiplicity of grains depending on the size of A and B, the size of the boxes. So recall that when the size of the boxes are not given to us, it's given by the set of row tubes. So the first simple, not so simple case is that when A equals to B equals to rho, so that's when the boxes are the minimal possible. Each box now shrink to just a single tube. So what happens when A and B equals to rho? So I should say that we are going to apply factoring proposition to the set of grains. And obtain A times B times 1 boxes. So when A and B equals to rho, then the grains will become just the set. So now I'm ignoring this refinement, assume T prime is just T for simplicity. When A equals to B equals to rho, then G equals to W. And W is satisfied convex. And then W satisfies the Kakeya-Wolf axiom. So this means that the grain itself satisfies the Kakeya-Wolf axiom. I know this is becoming a little technical, but are there any questions about the statement of the proposition and when we apply it, this special case means that the grains is Kakeya. Nothing. So that's the power of the proposition. Also, that's the key idea underlying the recent development. So we find a structure theorem after sufficiently many pigeonholing. For any set, we could find some structure from the set. And of course, there will be many parameters that come with it, but then we are going to analyze the situation depending on the parameters. Are there any more questions? So when AB equals to rho, then the grains is cast out. This is nice because, so if we still remember this decomposition, mu t is less or so the multiplicity of tubes is less or equal than the number of thin tubes in a thick tube passing through a point times the number of grains passing through a point. So this picture is this one. So we know that G is cast out, and this is also cast out, so we can apply induction. So the induction hypothesis says that for any set of tubes satisfying the cast-out Wolff axiom, the multiplicity is bounded by the number of tubes to the sigma. So mu t is now, this guy also satisfies the cast-out Wolff axiom. So this is the multiplicity mu t rho is bounded by the number of thin delta tubes inside t rho to sigma. And we also just said that in the special case when the grains is cast out, then the multiplicity, the number of grains passing through each point, is bounded by the number of grains to sigma. So here is where we use non-stickiness, because when T is non-sticky, we have a lot of rho tubes. And also by the fact that when something is cast out, there are not that many grains. So remember, each grain after rescaling is a rho tube. So if the set of grains is cast out, this means that the set of grains that matters to us is less than rho to the minus 2. So the number of grains is much less than the number of rho tubes. And this plug-in means that the number is much less than the number of rho tubes to sigma. So in total, this says that the number of tubes through each point is much less than the number of tubes to sigma. So also recall that after pigeonholing, we can assume that the number of tubes is approximately the number of delta tubes inside T rho times the number of rho tubes. So this holds true in general after pigeonholing. And so at this point, we have finished one case. When AB equals to rho, we show that the multiplicity is in fact much smaller than what this induction predicts. So in this special case, then we are done. Are there any questions? Okay, so there are, of course, many other cases, and that's why the problem is difficult. And also that's why the induction is quite involved. So another case is that when A is much larger than rho, so this is again our box. When A is much larger than rho, means that the box is a lot thicker than a rho tube. So here we use our, so remember that the theorem we want to prove, and that's also the intuition we have, is that from the factoring proposition, we know that the thin tubes inside, the rho tubes inside each box satisfies the Frossman-Wolff axioms. So the theorem we want to prove says that if something satisfies Frossman-Wolff axiom, then they should be quite dense and they should fill out the box. So intuitively, this says that the rho tubes should essentially fill out this A times B times 1 box. And this says that if we take a typical A ball that intersects this box, it should be quite full. And so the idea is that instead of estimating the multiplicity, we're going to estimate the local density of the Kakeya set. So when the thickness of the box is much larger than rho, then we can just thicken everything to a larger scale and then apply induction. So that's the idea for the second special case. We are not done yet, but are there any questions about the second special case? Okay. And the third case is where the problem becomes more interesting. The third case is that the boxes are as thick as the row tube. So we don't gain anything by thickening to the thickness of the box because we are not thickening anymore. But the box are a lot wider. So A is approximately rho, but B is much larger than rho. Then what does this mean? Here, since we know that the set of tubes is satisfy Frostman-Wolf axiom, so it fill out this very flat box. So this is 4. And this gives us a new grain decomposition of the union of tubes. So here, this picture, quite similar to the sticky case, the union of tubes will become a union of those slabs. Sorry, I shouldn't say slab. Those thin boxes that's like a plank. So it's wider than. And now we are going to study how those planks intersect. So those planks is the previous W. So A B times A equals to rho. And after rescaling, they become delta over rho. So this 1 becomes delta over rho, and then this rho becomes delta, and B becomes B times delta over rho. So if we go back to the previous Kakeya set, this says that the union of those tubes becomes the union of those thin planks. And the next step is to try to understand how the thin planks intersect. So again, imagine like we have let's say we have two iPhones that two phones that we want to, not two, but suppose we have many phones that we want to compute the volume of their union. So it's natural to split into two cases. One case is that a typical intersection of those phones are like transversal. So that is the transversal intersection case. So as you can see, when two things intersect transversely, or maybe many things intersect transversely, at a typical point, you have other planks that goes this way. So this means that locally, it should fill out a 3-dimensional small ball. And this is, again, we can use the thickening argument. So the Kakeya set locally fill out like a thicker ball. So we can just thicken to this larger scale and apply induction. That's what happens for the transverse case. Are there any questions? Okay. There is another case that's called the tangential case, means that if the typical intersection goes this way rather than this way. So this is a tangential intersection. Because they are tangential intersection, for this box, we call them plank when the box are really thin. For this plank, all the planks that intersected tangentially should lie inside some flat slab. So that is the yellow thing, because this have some planar direction, and when they intersect tangentially, they have to sort of also more or less coplanar. And if we organize those planks according to this yellow box, then the only other planks that matters to it are the planks that's tangential and contained in the yellow box. So we could rescale everything, rescale this yellow box. It turns out that when they intersect tangentially, the size of the yellow box would make sure that the planks, after rescaling, become a row tube, maybe some other row, becomes a tube again. So this picture, it becomes, so in the tangential case, this picture becomes a new version of the grain picture that is here. So we are going to repeat the same argument, and this is why the induction becomes somewhat complicated. So we are going to repeat the whole argument, and then and this will stop at some point. So let's summarize our winning strategies. So the first case, when the grain is Katz-Tau, satisfies the Katz-Tau-Wolff axiom, we could show that the multiplicity is small, and we are done. And the second winning strategy is that if we could, so these are the union of tubes. If we can say that for a typical larger ball that intersected, the union of tubes fill out this ball or has large density in those balls, then we can just, let's say, apply induction and thicken everything to the radius of the ball. And this we also gain because the density is large. So the second winning strategy is when we have large local density. And the third winning strategy is related to the last case. So when this, like we have this thin box but wide box, but becomes wider, and this is filled out. So the last winning strategy is that when the width becomes so large, the grains become wider and wider. So when the grains becomes long and so becomes like slabs, then imagine how to understand if we have a set of slabs, like slab means neighborhood of two planes. If we have a set of slabs that intersect in R2, and we can also define similar things as the set of slabs satisfies the Katz-Tau-Wolff axiom or something similar, then we can use just the L2 argument we have studied in the first lecture to give a nice bound on the union, on the volume of their union. So the third case is when I say that we have to stop somewhere nice. So that is the third case. When the grains become wider and wider, we could finish the argument using the L2 Cordoba estimate. Yeah. Yes, exactly. In the third case, what I didn't say is that when A is rho and B is much larger than A, this is like this new box. I will also call it grain, and that's when the grain becomes wider. Yeah, so that's the key winning strategies. Yeah, I guess I will stop here. Thank you very much for your attention.